Hello and welcome to our Le Chatelier's principle video. There's a lot to chew on in the PowerPoint, and so I would recommend highly that you take a look at it. And certainly, if you have an iPhone, view that PowerPoint in Keynote. There's some really important information or animation, I should say, to see there. It's really key. So here we have a reversible reaction, and we could say that it's at equilibrium. We are given this bit of detail where it says where delta H is equal to 30 or 300 kilojoules, and they're indicating that that's positive. So we sort of have to reach back into kinetics and ask ourselves, is this endothermic or exothermic? Which side, where would we be putting the heat? Like, is heat acting as a reactant or is heat acting as a product? And so in the case where the change in heat is positive, this means that energy is flowing into the system. In the case where it's negative, energy is flowing out, so that would be your exothermic reaction. In the case where it's positive, we're actually having energy flow into the system, and this is endothermic. So for an endothermic reaction, I like to think about it almost as if it is a reactant, because you need to have, X number of kilojoules for that forward reaction to occur. You also need heat for the reverse reaction, but this, in terms of the difference, will be greater on the reactant side. So now let's stress the system. So after each stress, we are going to just kind of reset it, I guess. So we have achieved equilibrium here with our reaction, and what we want to do is pump the vanadium 3 ion in. So we want to increase the concentration of the vanadium 3 ion. So in terms of what is the effect, we can imagine that this is sort of growing larger if you watch that PowerPoint, so you've got this really large vanadium. And basically at equilibrium, it doesn't want to support that. So at equilibrium, it wants to kind of return to some kind of normal or new normal. And so it needs to relieve this stress, this whole bunch of extra vanadium. The best way equilibrium can deal with that is by using it up. So if you have this increase of concentration, that forward reaction will be occurring more often, and you will end up seeing a shift to the right. So I'm just going to abbreviate this, and I'm going to kind of use my key down here. So I'm going to say shift right. So, and that shift, it's towards the products. And so which of the reactions are favored? In this case, we would see like a higher forward reaction occurring. So we would see that forward reaction, shifting the equilibrium to the right, because we want to relieve this stress. Now, my final column is just sort of another way of asking similar question using Le Chatelier's principle, and that's to say, what's the effect on the concentration of the bromine ion? So if we add some vanadium, if we increase the concentration of one of the reactants, and we see the forward reaction be favored, where the shift is towards the products, we would end up seeing more of this created. So we would visually see an increase in the bromine ion. If we stress the system by cooling, air quotes, cooling it down, not a thing. So what we are actually doing is removing the heat. That's the same as cooling it down, but yes. So if we're removing the heat, and you could think about that animation as taking that heat and just making it a little tiny mini heat. How does the system want to relieve that stress? Because now it doesn't have the heat required in order for the forward reaction to occur. So it relieves that stress of having that mini heat by replenishing the heat by favoring the reverse reaction. So we're going to see a shift left, which means it'll be a shift towards the reactants, which is considered the reverse reaction. What's the effect on the bromine ion if we start cooling down the system? Well, if the reverse reaction is favored and that one is happening more often, then this is getting used up. So the effect on the bromine ion is that it decreases. Okay, reset. Let's remove some Br2. So let's take some of that bromine, those bromine molecules, and remove them. It could be by a drying agent. It could be captured in some other way, but we're removing that from the system. And so what we would see is we would see significantly less of that. The concentration would be decreased in the reactants. Again, we're going to want to shift back left to refill that bromine that has been removed. So if it's as if a hole has been created and now the reverse reaction is trying to fill it up. So we would see a shift towards the reactants. We would see the reverse reaction. And in terms of the Br ion, again, as the reverse reaction is really happening a lot, we would see the Br ion decrease. So the addition of a catalyst. This is very interesting because we know from our kinetics unit that catalysts will speed up a reaction in terms of moving from forward to or from reactants to products. But in terms of a reversible reaction, we would actually see the effect of the catalyst creating a faster reaction on both pieces. So not only let's add a catalyst here. Not only will the activation energy be lower for the forward reaction, but also for the reverse. So the forward reaction will actually happen faster than it normally would, but also the reverse reaction would happen faster than it normally would. So all in all, we would say here that there's no shift. It's not shifting left, it's not shifting right. There'd be no change. And in terms of the bromine, even though it's actually getting used up faster, it's also getting created faster. So here we'd see no change. Okay. If we increase the pressure, this is very, very interesting. So if we increase the pressure, we want to look at the nature of the compounds and elements that we're dealing with in our reaction. And when we look, we see they're aqueous, liquid, aqueous. Pressure is not going to have an effect on solid, liquid, or aqueous reactants or products. That's only going to have an effect on gases. So straight away, an increase in pressure in this one, this is a trap. No change, no shift. So let's just take a second and pause there. Let's just pretend that they were all gases. How would we answer this question if they were gases? What we'd want to do is add up the number of moles on each side. So assuming it's gas, 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 we'd have 2 plus 2 plus 1. So we'd have 5 moles of reactants. And here we'd have 2 plus 4 is 6, plus 2 is 8. So 5 moles here, 8 moles here. If we're taking all of this and squeezing it down, we're increasing the pressure, which means we're decreasing the volume. Which side are going to be bumping up more often? Because the increase of pressure affects both equally. So we have 5 as reactants, 8 as products. We want to shift towards the side with the least number of moles. So the thinking is the side with 8 moles, now there's more stuff there, like literally more stuff. They're going to be hitting up against each other. The successful collisions will happen more often. Therefore, the reverse reaction is going to be favored in this case. And it will be a very clear shift left in the case where they were gaseous, but of course they're not. So let's move on. Last one. The removal of the VO2 plus ion. So we're taking a product and we're decreasing the concentration in it. So we kind of made it mini. How do we relieve this? The only way to relieve this is to allow the forward reaction to occur and sort of refill. So we would call this a shift right. We would see the equilibrium shift to the right as this decreased amount starts to get filled. We would want to also call this that we're going towards the products. And you might also consider this to be a forward reaction being favored. So what happens when we refill this and we have a highly active forward reaction? We would actually see our amount of BR increase.